Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. Today we will discuss steam and condensate systems. We will also discuss process equipment such as the steam side of reboilers, steam turbine surface condensers, condensate recovery systems, derators, the steam side of shell and tube steam preheaters. A few of the nasty features of this sort of process equipment we discuss are condensate backup, accumulation of carbon dioxide, steam hammer, blown condensate seals, steam reboilers. When considering the steam side of steam-heated reboilers, it is best to think about the reboiler as a steam condenser. The steam, at least for a conventional horizontal reboiler, is usually on the tube side of the exchanger, as shown in this picture. The steam is on the tube side because the shell side was selected for the process fluid. If the reboiler is a thermosiphon or natural circulation reboiler, then low process side pressure drop is important. For a horizontal reboiler, it is easiest to obtain a low pressure drop for the fluid being vaporized by placing it on the shell side. The steam enters through the top of the channel head of the reboiler. Any superheat in the steam is quickly lost to the tubes. Superheating steam does very little in increasing heat transfer rates in a reboiler. Actually, when considering the temperature difference between the steam and the process fluid, it is best to use the saturated steam temperature as the real temperature at which all the heat in the steam is available. For example, assume the following steam flow to a reboiler. 1000 pound/hour of 100 psig steam. 400 degrees Fahrenheit steam inlet temperature. 300 degrees Fahrenheit condensate outlet temperature. The 100 psig steam condenses at approximately 320 degrees Fahrenheit. The heat available from the steam is the superheating equals 400 to 320 degrees Fahrenheit times 0.5 BTU per pound degree F times 1000 BTU per pound equals 40,000 BTU per hour. Condensing equals 900 BTU per pound times 1000 BTU per hour equals 900,000 BTU per hour. Subcooling equals 320 to 300 degrees Fahrenheit times 1.0 BTU per pound degree F times 1000 BTU per hour equals 20,000 BTU per hour. Total reboiler duty equals 960,000 BTU per hour. This calculation is typical in that 94% of the heat is liberated at the 320 degrees Fahrenheit condensing temperature of the saturated steam. Another way of stating the same idea is that a steam reboiler depends on latent heat transfer and not on sensible heat transfer. Condensing heat transfer rates. When a vapor condenses to a liquid, we say that the latent heat of condensation of the vapor is liberated. In a steam reboiler, this liberated heat is used to reboil the distillation tower. When a vapor, or more commonly a liquid, cools, we say that its sensible heat is reduced. For a small or slight temperature change, the change in latent heat might be large, while the change in sensible heat will be very small. Heat exchange provided by sensible heat transfer is improved when velocities are higher. Especially when the heating fluid is on the tube side of an exchanger, sensible heat transfer rates are always increased by high velocity. Heat exchange provided by latent heat transfer is improved when velocities are lower. It is my experience that this loss of heat transfer at high velocity is quite large when steam is flowing through the tube side of an exchanger. Theoretically, this happens because the condensing film of steam is blown off the tube surface by the high vapor velocity. This improved heat transfer rate, promoted by low velocity, applies not only for condensing steam but also for condensing other pure component vapors. And since condensation rates are favored by low velocity, this permits the engineer to design the steam side of reboilers and condensers in general for low pressure drops. For example, if we measured the pressure above the channel head pass partition baffle shown in picture, we would observe a pressure of 100 psig. The pressure below the channel head past partition baffle would typically be 99 psig. Blown condensate seal. The picture shows a common type of reboiler failure. The steam trap on the condensate drain line has stuck open. A steam trap is a device intended to open when its float is lifted by water. The steam trap remains open until all the water drains out of the trap. Then, when there is no more water to keep the trap open, it shuts. But if the float sticks open, steam can blow through the steam trap. This is called a blown condensate seal. The average vapor velocity through the tubes will then accelerate. If the steam trap is passing a lot of steam, the velocity of steam in the tubes increases a bit. Blowing the condensate seal due to a faulty steam trap causes a loss in reboiler duty of 50% or more. This is due to the increased steam tube side velocity, reducing the rate of condensation of the steam, and hence reducing the rate of liberation of the latent heat of condensation of the steam. Condensate backup. What would happen to a steam reboiler if the float in the steam trap became stuck in a partly closed position, or if the steam trap were too small? Water, that is, steam condensate, would start to back up into the channel head of the reboiler, as shown in this picture. The bottom tubes of the reboiler bundle would become covered with water. The number of tubes exposed to the condensing steam would decrease. This would reduce the rate of steam condensation and also the reboiler heat duty. Meanwhile, the tubes covered with stagnant water would begin to cool. The steam condensate submerging these tubes would cool. This cooled water would be colder than the saturation temperature of the condensing steam. The tubes would then be said to be submerged in subcooled water. We can see, then, that either condensate backup or blowing the condensate seal will cause a steam reboiler to lose capacity. If you think either of these two problems could cause a loss in reboiler duty, try opening the bypass around the steam trap. If the reboiler duty goes up, the problem was condensate backup. If the reboiler duty goes down, the problem might be a blown condensate seal. If it looks like a blown condensate seal problem, close the steam trap bypass. Then partially close the valve downstream of the steam trap. If this increases the reboiler duty, a blown condensate seal failure is proved. Steam flow control. The flow of steam to a reboiler can be controlled by using a control valve on either the W1 steam inlet line or the E2 condensate outlet line. The picture shows a control valve on the steam inlet line. The rate of steam flow to the reboiler is not really controlled directly, however, by this control valve. The actual rate of steam flow to the reboiler is controlled by the rate of condensation of the steam inside the tubes. The faster the steam condenses, the faster it flows into the channel head. The function of the control valve is to reduce the steam pressure in the channel head of the reboiler. For example, in case 1, described below. 160 psig steam supply header pressure. Delta P across control valve equals 60 psi and the control valve is 40% open. 100 psig steam pressure, condensing at 320 degrees Fahrenheit, in the channel head. Shell side reboiler temperature of 240 degrees Fahrenheit. Steam flow equals 10,000 pound per hour. Temperature difference between the condensing steam and the boiling process liquid is then 320 to 240 degrees Fahrenheit equals 80 degrees Fahrenheit. This is called the temperature difference driving force, or delta T. Now the rate or heat duty of steam condensation is termed Q equals A times U times delta T, where A equals surface area of the tubes, which are exposed to the condensing steam in square feet. U equals heat transfer coefficient, a constant, describing the rate of condensation of steam on those tubes exposed to the condensing steam BTU per hour per square feet degree F. Delta T equals temperature difference between the shell and tube sides, degree F. Q equals heat exchanger duty, BTU per hour, for the preceding equation in case 1, 10 million BTU per hour. In case 2, the shell side reboiler temperature rises from 240 to 280 degrees Fahrenheit. One reason for such a rise in temperature could be an increase in tower pressure. Now delta T equals 320 to 280 degrees Fahrenheit equals 40 degrees Fahrenheit. Looking at the equation on the previous slide, it looks as if Q will drop in half to 5,000 BTU per hour, which is about the same as 5 million BTU per hour. Thus, the flow of steam to the reboiler has been cut in half, even though the control valve position has not moved. You might have noticed how we have used 1 million BTU per hour of heat interchangeably with 1,000 pound per hour of steam. This is approximately correct for low-pressure steam. To consider a third case, we wish to maintain the original 240 degrees Fahrenheit shell side temperature, but to increase the steam flow from 10,000 to 15,000 pound per hour. This will force the steam inlet control valve to open. As the control valve opens, the pressure in the channel head rises from 100 psig to the full steam header pressure of 160 psig. At this pressure, steam condenses at 360 degrees Fahrenheit. The new delta T is then 360 to 240 degrees Fahrenheit equals 120 degrees Fahrenheit. This new temperature driving force is 50% greater than the first case's driving force of 80%. Hence the rate of steam condensation also increases by 50%, from 10,000 to 15,000 pound per hour. In case 1, the steam inlet control valve was 40% open. In case 3, let's assume that the inlet control valve is 70% open. If we open the control valve to 100%, the steam flow will not increase at all. Why? Because once the steam pressure in the channel head rises to the steam header pressure, no further increase in steam flow is possible, regardless of the position of the inlet control valve. Condensate control. Once the steam pressure in the channel head in this picture falls to the pressure in the condensate collection header, the steam trap can no longer pass condensate. Water will back up in the channel head and waterlog the lower tubes in the tube bundle. This will lead to unstable steam flow control. This is especially true if the steam supply pressure is less than 20 psig above the condensate collection header pressure. It is better not to use a steam inlet control valve when using low-pressure steam. The channel head pressure will then always equal the steam header supply pressure. The flow of steam to the reboiler can then be controlled only by raising or lowering the water level in the channel head, as shown in this picture. This sort of control scheme will work perfectly well until the water level drops to the bottom of the channel head. If the condensate drain control valve then opens further in an attempt to increase steam flow into the reboiler, the condensate seal is blown, and the reboiler heat duty drops. A better design is shown in this picture. In this scheme, a condensate drum is used to monitor the level in the channel head. As the drum level is drawn down, the number of tubes in the reboiler exposed to the condensing steam is increased. However, when the water level drops to the bottom of the channel head, the level sensor in the condensate drum assumes control over that is overrides the condensate flow controller and prevents loss of the condensate seal. One important feature of this picture is the condensate drum balance line. Note that this line is connected below the channel head pass partition baffle. This ensures that the pressure in the channel head below the pass partition baffle and the pressure in the condensate drum are the same. If these two pressures are not identical, the level in the condensate drum cannot represent the level in the channel head. For this reason, never connect the condensate drum vapor space to either the steam supply line or the top vent of the rebuilder's channel head. Carbonic acid corrosion. Steam produced from demineralized water is largely free of carbonates. Steam produced from lime-softened water will be contaminated with carbonates that decompose in the boiler to carbon dioxide. As the steam condenses in a reboiler, the CO2 accumulates as a non-condensable gas. This gas will be trapped mainly below the channel head pass partition baffle, shown in this picture. As the concentration of CO2 increases, the CO2 will be forced to dissolve in the water. H2O plus CO2 equals H2CO3 equals H positive, HCO3 negative. That is, carbonic acid will be formed. Carbonic acid is quite corrosive to carbon steel. Reboiler tube leaks, associated with steam side corrosion, are almost certainly due to carbonic acid attack. Venting the channel head through the balance line shown in this picture will prevent an excessive accumulation of CO2. This is done by continuous venting from the top of the condensate drum. For every 10,000 pound/hour of steam flow, vent off 50 pound/hour of vapor through a restriction orifice placed in the condensate drum vent. This is usually cheaper than controlling reboiler steam side corrosion with neutralizing chemicals. Often the problem with CO2 accumulation inside the channel head results not so much in corrosion, but in the loss of heat transfer. This is due to the tubes below the bottom pass partition baffle filling with non-condensable CO2 gas. You can observe this problem even in plants using demineralized boiler feed water. Venting from beneath the bottom pass partition baffle will restore heat transfer rates. Venting above the pass partition baffle or from the top of the channel head is futile. Unfortunately, most such channel head vents are installed on the top of the channel head, and thus are completely ineffective. Channel head leaks. Varying the steam to condensate interface level to control the reboiler duty will promote steam leaks in the channel head to shell flanged closure. This is caused by the thermal cycling and stresses that result from constantly varying the level of condensate in the channel head. However, when low-pressure steam, less than 60 psig, is used, this becomes a minor problem, which may be safely ignored. When high-pressure steam, greater than 100 psig, is used, rather significant leaks of hot condensate and steam can be caused by a variable condensate level in the channel head. For such higher pressure steam sources, control of steam flow with condensate backup, as shown in these pictures, is best avoided. Condensate collection systems. How much steam condensate is your plant recovering? 70% is considered pretty good, and 30% is, by any standard, pretty awful. As condensate collection flows are rarely metered, here is a really good way to make such an overall measurement: ST equals steam, TR equals treated water. 1. Determine ST, the pound/hour of steam raised in the whole plant. 2. Determine TR, the pound/hour of softened or demineralized treated water flowing to the derators. 3. The percent of condensate recovery is then 100% minus 100% TR divided by SC. Loss of steam condensate to the plant sewer is environmentally wrong and wastes money for water treating chemicals and energy. The principal reasons why steam condensate is lost to the sewer are: it creates steam or water hammer in the condensate collection system. Back pressure from the condensate collection lines creates control difficulties in steam reboilers or heaters. The condensate is contaminated with traces of dissolved hydrocarbons, phenols, NH3, H2S, etc. Water hammer. Steam or water hammer, more properly called hydraulic hammer, is one process plant phenomenon familiar to the general public. When trying to warm up the steam system of a large amine plant in your plant, you can hear more than hearing the crescendo of crashes due to steam hammer. The cause of steam hammer is illustrated in this picture. In general, hydraulic hammer is caused by the sudden conversion of the velocity of a liquid into pressure, causing a surge of pressure inside a piping system. Steam hammer is caused by the creation of localized cool areas in piping systems containing saturated steam. For example, when first introduced into idle pipes, the steam condenses rapidly upon encountering a length of cold piping. This creates slugs of water. The continuing rapid but localized condensation of steam further downstream creates areas of low pressure or even a partial vacuum. The slugs of water rush to these areas of low pressure. Or, more precisely, the pressure differences created by the localized condensation of the steam provide a source of energy to accelerate water in the steam system. When these rapidly moving slugs of water impact an elbow or T-junction, the vibrations and noise of steam hammer result. Introducing condensate from high-pressure steam traps into the low-pressure condensate collection system will generate steam. For example, passing 1,000 pound/hour of condensate from a 160 psi G reboiler into a 20 psi G collection system will generate about 100 pound/hour of steam. More importantly, the volume of flow will increase from 20 cubic feet per hour to over 1,000 cubic feet per hour, as a result of flash vaporization. If water at, say, 200 degrees Fahrenheit from a low-pressure trap enters the piping, then any flashed steam will rapidly condense and create an area of low pressure. Slugs of water will rush to this low-pressure area, crashing into elbows and piping fittings, thus, the origin of steam hammer. Operators stop steam hammer by dumping either the hot condensate from a high-pressure steam trap or the colder condensate from a low-pressure steam trap to the sewer. Either way, the condensate is no longer recycled to boiler feed water. The sort of design required to collect condensate without steam hammer is illustrated in this picture. Basically, hot, high-pressure condensate is collected in a dedicated system. The flashed steam from this system is recovered as low-pressure steam. The resulting water is then passed into the low-pressure condensate recovery piping system along with water flowing from the low-pressure steam traps. Condensate backup in reboilers. Operators who have problems with loss of reboiler capacity often attribute these problems to condensate backup. This is usually true. To drop the level of water out of the channel head, either the steam trap or the condensate drum is bypassed by putting the condensate to the sewer. Sometimes the float of the trap is sticking, but mostly the difficulty is in erratically high pressure in the condensate collection piping. Our guess is that the engineers who designed these collection systems do not anticipate the large volume of steam generated from flashing, high-pressure condensate. Condensate pumps are sometimes used to overcome such back pressure problems. However, these pumps are often not kept in good repair, and condensate is still lost to the sewer. Eliminating the steam inlet control valve of the type shown in this picture has helped recover condensate from many reboilers supplied with low-pressure steam. Contaminated condensate reuse. Much of the steam consumed in process units comes into direct contact with the process streams. A few examples are steam vacuum jets, catalyst lift steam, stripping steam, vessel purge steam. For corrosion and safety reasons, the condensate recovered from these sources is best not returned to the deaerator for use as boiler feedwater. However, there are no unchangeable rules in the process industry. Some plants collect all their contaminated steam condensate streams from reflux drums and from a vacuum tower hot well system. Without even steam stripping, the collected condensate is recycled back to the steam boiler. It's true only where low pressure, 100 psig, steam is generated. It's true the steam so generated is not used in a turbine or in any chemical process. But on the other hand, they had been doing this for 20 years without any ill effects. Depending on the contaminant, the condensate may be reused for a number of services. Our favorite reuse of such contaminated condensate is as a replacement for velocity steam in the heater tube passes of a fired furnace. There is little danger in injecting a controlled amount of water into a furnace inlet when using a properly designed metering pump. Such pumps typically have a capacity of 1 to 10 GPM and provide a set flow regardless of the discharge pressure. The injected water flashes immediately to steam inside the furnace tubes. Deaerators. The humble deaerator, operated by the utility department, is an interesting and important component of any process facility. Oxygen is a highly corrosive element and if left in the boiler feedwater would rapidly oxidize the boiler's tubes. The dissolved air left in boiler feedwater, BFW, is stripped out with steam in the deaerator shown in this picture. The cold BFW has been taken first from the river and then filtered to remove sand and sediment. Removal of the bulk of the calcium salts that would cause hardness deposits in the boilers is often accomplished by hot lime softening. If excess CO2 gas appears in downstream units consuming the steam, it is the fault of the lime softening, not the deaerator. This picture shows that the cold BFW has been heated to 160 degrees Fahrenheit, from the 90 degrees Fahrenheit lime softener effluent. This is an excellent way to save steam to the deaerator. Usually, heating river or well water above 130 degrees Fahrenheit would cause the laydown of hardness deposits inside the cooling water tubes, assuming the cooling water to be on the tube side. But using softened water as a cooling water supply permits that water to be easily heated to 160 degrees Fahrenheit without fear of precipitating hardness deposits. Thus, softened or demineralized cooling water can also be used as boiler feed water, and about 40% of the deaerator steam requirements are then saved. Most of the steam supplied to a deaerator is used to heat the 160 degrees Fahrenheit BFW to 230 degrees Fahrenheit. This is the boiling point of water at 10 psig, which is the pressure in the deaerator. The water in the deaerator must always be at its boiling point. It is impossible to steam strip air out of water below its boiling point temperature. The 160 degrees Fahrenheit BFW is efficiently mixed with the incoming steam in what is effectively a small, vertical stripping tower mounted above the large deaerator drum. The majority of the steam condenses by direct contact with the 160 degrees Fahrenheit BFW, and in so doing, the latent heat of condensation of the steam is used to increase the sensible heat content of the 160 degrees Fahrenheit BFW to 230 degrees Fahrenheit. A small amount of steam is vented from the top of the stripping tower to the atmosphere. Using a gate valve, with a hole drilled through the gate, is a simple way to control the venting rate. The dissolved air in the cold BFW is vented with this steam. The stripped 230 degrees Fahrenheit BFW drains into the large deaerator drum. This drum simply provides residence time for the high-pressure BFW pumps, which supply water directly to the boilers. Recovered steam condensate, which should be air-free, is fed to this drum through a separate nozzle. Deaerator flooding. An operator reported loss of the water level in the deaerator drum. The level control valve shown in this picture would open 100%, but this drove the level down even faster. The operator reported that the only way he could restore the water level would be to mostly close the water makeup level control valve. On the surface, this story sounds crazy. But let's see what happened. This deaerator had been designed for a much smaller flow of 160 degrees Fahrenheit BFW and a much larger flow of hot steam condensate than our current operations. The cold BFW feed line had been oversized, but the steam line was of marginal size. As the demand for hot BFW increased, the cold BFW level control valve opened. This reduced the temperature and pressure in the deaerator drum. In response, the steam pressure control valve also opened. But when the cold BFW level control valve was 40% open, the steam pressure control valve was 100%. Steam flow was now at its maximum. The pressure inside the deaerator started to drop, as there was not enough steam flow to keep the water in the drum at its boiling point. The reduction in the deaerator pressure increased the volume of steam flow through the bottom tray of the stripping tower. Why? According to the ideal gas law, volume is inversely proportional to pressure. As the pressure of the flowing steam declined, the steam's volume increased. The larger volume of steam flow resulted in a higher vapor velocity to the stripper trays 1 through 3. This caused the bottom stripper tray to flood. After a few minutes, the flooding forced cold BFW out of the atmospheric vent. The level in the deaerator drum then fell. The cold BFW level control valve opened further, driving down both the temperature and the pressure in the deaerator drum. The volume and the velocity of the steam flow to the stripper also increased, and the flooding became progressively more severe. The only way the operator could restore the water level was to reverse this process. He manually restricted the flow of cold BFW through the level control valve. This raised the stripper pressure and stopped the flooding. The problem was corrected by increasing the temperature of the cold BFW to 190 degrees Fahrenheit. Note that the key to solving this problem was observing the loss of water through the atmospheric vent. Sometimes, as far-fetched as an operator's description of a problem seems, it is still correct. Steam turbine surface condensers. Steam used to drive a turbine can be extracted at an intermediate pressure for further use of the low-pressure steam. Rarely is the steam vented to the atmosphere, as this wastes steam, and the condensate is also lost. Many turbines exhaust steam under vacuum to a surface condenser. The lower the pressure in the surface condenser, the greater the amount of work that can be extracted from each pound of steam. Discounting the presence of air leaks, the temperature inside the surface condenser determines the pressure of the steam exhausting from the turbine. This pressure is the vapor pressure of water at the surface condenser outlet temperature. The original steam condensers were barometric condensers, which were used to increase the efficiency of the steam-driven reciprocating beam engines by a factor of 10. Exhaust steam is mixed directly with cold water. As this creates a vacuum, the barometric condenser must be elevated about 30 feet above grade. The mixed condensate and cooling water drains through a pipe called a barometric leg, hence the name barometric condenser. The surface condenser is an improvement on the barometric condenser because it permits recovery of clean steam condensate. Other than this factor, the old-fashioned barometric condenser is more efficient than the more modern surface condenser. This picture shows the type of surface condenser most widely used on older steam turbines. Note that it has both a vapor and a liquid outlet. The turbine is located above the surface condenser. The wet exhaust steam flows down into the top of the condenser shell. Note that the exhaust steam from an efficient turbine will contain several percent of water. The shell side pressure drop of the surface condenser is quite low. The vapor outlet flow consists of air drawn into the system through leaks, CO2, and a small amount of uncondensed steam. The weight flow of vapor from the top of the condenser is 1% or less than the flow of condensate from the bottom of the condenser. The vapor is drawn into a steam jet. The steam condensate flows into the boot or hot well. The water in the boot is slightly subcooled. This is accomplished by a pair of baffles that create a small zone of condensate backup. The subcooled condensate, cooled to perhaps 10 degrees Fahrenheit below its boiling or bubbling point, is easier to pump. As the pressure in the hot well is subatmospheric, a hot well pump typically develops a delta P of at least 30 to 50 psi. If the hot well pump cannot handle the required condensate flow, the water level in the well will back up. The temperature in the hot well will go down as the lower condenser tubes are submerged. But this will reduce the surface area of the condenser that is exposed to the condensing steam. The condenser outlet temperature will therefore rise, and so will the surface condenser pressure. This reduces the horsepower that can be recovered from each pound of the motive steam flowing to the turbine. The turbine will then slow down. One common error made in monitoring the performance of surface condensers is the practice of considering the hot well temperature as if it were the true condensing temperature. It is the vapor outlet temperature that is the real surface condenser temperature. A decrease in the hot well temperature resulting from a high hot well water level is not an indication of improved condenser performance. It is a sign of reduced condenser capacity. Air-cooled surface condensers. This picture shows a surface condenser elevated above the steam turbine. This creates an additional problem in that moisture from the turbine exhaust steam will accumulate in the bottom of the turbine case. A special drain line from the turbine's case is needed to prevent condensate backup from damaging the spinning wheels. One such turbine in a refinery would not drain properly. In order to push the condensate out of the turbine case, the operators were forced to raise the surface condenser pressure from 100 to 250 millimeters of mercury, that is, 20 inches of mercury vacuum, in the American system. Note that the balance line shown in picture keeps the pressure in the turbine case and the condensate drum, into which the turbine case is draining, the same. The turbine case pressure was increased by raising the pressure in the air-cooled surface condenser. This was accomplished by shutting off several of the air fans, which, in turn, increased the condensing temperature of the exhaust steam. But why would raising the turbine case pressure drain the turbine anyway? After all, increasing the surface condenser pressure also increased the pressure in the drum that the turbine case drained to. The answer is revealed when the available data are converted to consistent units. The 250 millimeters of mercury turbine case pressure is equal to a height of water of 11 feet. Atmospheric pressure at plant location was 14.5 psia that day, which is equal to 33 feet of water. The difference between atmospheric pressure and the pressure in the turbine case, expressed in feet of water, is then 33 feet to 11 feet equals 22 feet. This turned out to be the exact elevation difference between the water level in the turbine case and the only flange on the drain line, from the turbine case to the drum below. This flange was found to be leaking. If the water head pressure at the flange became less than atmospheric pressure, then air was forced into the drain line. The bubbles of air expanded as they floated up the drain line into the turbine case. This prevented the water from draining freely through the drain line into the drum. Only by raising the turbine case pressure to pressure up the flange to match atmospheric pressure could this air leak be stopped. The flange leak was taped over, and the exhaust steam pressure dropped back to 100 millimeters of mercury. The steam required to drive the turbine fell by 18%. This incident is technically quite similar to losing the downcomer seal on a distillation tower tray. Again, it illustrates the sort of field observations one needs to combine with basic technical calculations. This is the optimum way to attack and solve process problems. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.